Now we will start to have a look at carbonyl-carbonyl condensation reactions. In this type of reaction, two carbonyl molecules react together to form one single organic product and a small molecule which is typically water. In general, this reaction takes place in two parts. In the first part, two aldehyde or ketone molecules react so that one molecule undergoes an alpha substitution and the other molecule undergoes a nucleophilic addition reaction. Then in the second part, the organic molecule loses water. There are different types of carbonyl-carbonyl condensation reactions. Reactions of two molecules of the same aldehyde or ketone are called aldol condensations, whereas reactions of two different aldehyde or ketone molecules are called crossed aldol condensation. And if the reaction is conducted with one molecule which contains two aldehyde groups or two keto groups which react with each other, the reaction is then called intramolecular aldol condensation. And in general, these reactions are very useful in organic synthesis as they yield a new carbon-carbon bond, and they can also be used to convert a linear molecule into a ring molecule. We will now start with the aldol condensations, and first of all, the aldol condensation of an aldehyde. In the first step, a base such as hydroxide abstracts an hydrogen of the aldehyde in alpha position, and hereby an enolate ion in water is formed. This enolate ion is a nucleophile and will then subsequently attack the carbon atom of the carbonyl group of the remaining aldehyde. And hereby an alkoxide ion is formed. This alkoxide ion has already a new carbon-carbon bond, and this bond is formed between the alpha carbon of one aldehyde and the carbon atom of the carboxyl group of the other aldehyde. The last step is then the protonation of this alkoxide ion, and hereby a beta hydroxyaldehyde, also called as aldol, is formed. Moreover, the hydroxide ion is regenerated. If we now compare the aldol condensation of an aldehyde with that of a ketone, we can directly see that we have exactly the same reaction mechanism. So we start with a deprotonation of an hydrogen at alpha position, this time on a ketone, and hereby we form water and an enolate ion. Subsequently, the enolate ion acts as nucleophile and attacks the carbon atom of the carbonyl group of the remaining ketone, and hereby an alkoxide ion with a new carbon-carbon bond is formed. The last step is then again a protonation of this alkoxide ion. Hereby a beta hydroxyketone is formed, and also the hydroxide ion is regenerated. All steps of the aldol reactions are reversible, and the position of the equilibrium depends on the nature of the carbonyl compound. For an aldehyde, the equilibrium usually lies more on the side of the aldol, whereas for a ketone, the equilibrium lies usually more on the side of the ketone. Hence, the conversion of an aldehyde into an aldol is usually faster compared to the conversion of a ketone into an aldol due to the higher reactivity of the carbonyl group of the aldehyde. In a second stage of the aldol condensation, the formed beta hydroxyaldehyde or beta hydroxyketone is heated with an acid or base catalyst in order to eliminate water. And here on top we have the step with an acid catalyst. So the elimination of water proceeds via the formation of an enol, followed by the elimination of water, which is a good leaving group. Finally, the oxygen gets deprotonated in order to regenerate the acid catalyst. Conversely, if a base catalyst is used, the first step is the abstraction of an alpha hydrogen. Hereby an enolate ion is formed, which then eliminates an hydroxide ion in order to form the stable product. This product contains conjugated carbon-oxygen and carbon-carbon double bonds. Also important, the E isomer is usually formed as this isomer is more stable than the Z isomer. Now let's talk about crossed aldol condensations. Crossed aldol condensations involve two different aldehydes or ketones, and if the two aldehydes and ketones can form enolate ions equally well and can both act as electrophile in nucleophilic additions, Then a mixture of all 4 possible aldol products will be formed in the reaction with a base at room temperature. This is, for example, the case for the reaction of propanol with butanol. And you can see here we form indeed 4 different aldol products. However, then you can only achieve a relatively low amount of one of the aldol products. Hence, it is desired to tune a reaction in that way that you can get only one product instead of a product mixture. And the crossed aldol condensation yields only one aldol product if only one of the carbonyls is able to form an enolate ion, or if the carbonyl compound, which cannot form an enolate ion, is more reactive to nucleophilic additions compared to the other carbonyl compound, which can form an enolate ion, or if the carbonyl compound that is able to form an enolate ion is added slowly to the reaction mixture. For example, the reaction of acetone with benzaldehyde yields only one product in the crossed aldol condensation. And if we have a look on acetone as well as benzaldehyde, we can see that only acetone has hydrogen atoms in alpha position. And here for the benzaldehyde, we can clearly see that there is no hydrogen in alpha position. Hence, it cannot form an enolate ion. That means the base will abstract a hydrogen atom in the alpha position of the acetone, and hereby only the acetone will form an enolate ion. Subsequently, this enolate ion can, in principle, react with either the acetone or the benzaldehyde. However, the carbon atom of the carbonyl group in the aldehyde is more electrophilic compared to that of the acetone. Hence, the enolate ion will react with the carbon of the carbonyl group in the aldehyde. Hence, the enolate ion will react with benzaldehyde. Additionally, acetone is added only dropwise in order to ensure the enolate ion reacts with the aldehyde, as there will be no excess of acetone in the reaction mixture. Finally, beta-hydroxyketone is heated with the hydroxide ions in order to eliminate water, and hereby the E-enone is formed as product and the base catalyst is regenerated. Let's turn now to the intramolecular aldol condensations. And in an intramolecular aldol condensation, the starting material, which contains 2 carbonyl groups, is heated with a base and a cyclic product will result. For example, the intramolecular aldol condensation of hexane diol starts with the deprotonation of a hydrogen atom in alpha position to form an enolate ion. And we can see here on this molecule that the alpha positions are identical. So there is no preferred hydrogen which can be abstracted by the base. Then we form, after this deprotonation step, we form an enolate ion and water. Subsequently, a nucleophilic addition of the enolate ion on the carbon of the remaining carbonyl group is conducted, and hereby a 5-membered ring is formed. In the following step, this 5-membered ring gets protonated, and finally, in the last step, the reaction mixture is heated in order to eliminate water, and hereby the cyclopentene product is formed and the base catalyst is regenerated. In theory, some dicarbonyl compounds could react to form a mixture of various sized rings. However, in practice, only 5- and 6-membered rings are formed, as those are the most stable ones. And this becomes clear if you have a look on the intramolecular aldol condensation of hexane 2,5-dione. We see here this hexane 2,5-dione, and we can see here that we have 2 different sites for the deprotonation alpha position. If we then deprotonate the different alpha positions, we end up with 2 different forms of the enolate ion. And then in the subsequent step, when the nucleophilic attack of the enolate ion on the remaining carbonyl group is conducted, you can see that from this enolate ion here on bottom, we will end up with a 3-membered ring, whereas from this enolate ion on top, we end up with a 5-membered ring. And as you already know, a 3-membered ring has a strong strain, and therefore 3-membered rings are not stable. Conversely, here on top, we form a 5-membered ring, which is stable. Then we continue with the intramolecular aldol condensation, and then we end up with cyclopentene molecule, which is called 3-methylcyclopent-2-ene-1-one.